Hi, my name is Jin. I'm going to present our paper MTG, which is Mapless trajectory generator with traversability coverage for mobile robots. The motivation behind this project is that instead of estimating the traversability of the large-scale observations, we directly generate representative trajectories to cover the traversable areas during the navigation. So there are two challenges. First, we want all the generated trajectories only lie in traversable areas. And the second, we want those trajectories as diverse as possible to cover the traversable areas. In this paper, we have three innovations. First, we propose a CVE-based architecture to generate diverse trajectories to cover all the traversable areas. And second, we provide the confidence of the generated trajectories. And third, we designed different loss functions to satisfy all the criteria. And for the first innovation, we propose a CVE-based architecture for trajectory generation. And in the architecture, we project the Gaussian embedding vector to multiple orthogonal vectors by linear transformation. So each of those vectors can be decoded into one trajectory. And we want each vector to represent one traversable area. But there could be the case in the figure that the number of traversable areas could be smaller than the number of generated trajectories. So in this case, there could be some redundant trajectories. But we don't want the redundant trajectories to be too diverse and lie in non-traversable areas. We want these trajectories to still lie in traversable areas, although those trajectories can be very close to the effective trajectories. So in order to know whether the embedding vector corresponds to a redundant trajectory or effective trajectory, it should have some information of other vectors. So we use the attention mechanism to calculate the relationship between the current embedding vector and all other embedding vectors. And then we put the relationship as a condition to the decoder to generate the trajectory. The second contribution is the confidence estimation. Because CVE-based architectures use Gaussian distribution as embedded information, so we can calculate the uncertainties by averaging the variances of the vector. The third contribution is about the loss function. The first loss function is the CVE lower bound. And for the reconstruction loss, we use Hausdorff function to calculate the distance between the ground truth trajectories and the generated trajectories. And the second loss function is the diversity loss function. And in this loss function, we encourage the effective trajectories as diverse as possible to cover more traversable areas. And we also want the redundant trajectories to stay close to the effective trajectories. And the third term is traversability loss function. This loss function is calculated by the distance between the non-traversable areas and the waypoints of the generated trajectories. So the total loss function is a combination of the three terms. And this is the quantitative result of our paper. So from the table, we can see that MTG has the highest traversability, and it also has the highest coverage of the traversable areas. And this is the quantitative result of our experiment. So in the real-world experiment, we use GPS to provide a really long distance target. And then in the trajectory selection, we have 5 candidates to select. And the selected trajectory should satisfy these two constraints. First, the trajectory should not be the least confident trajectory. And second, the selected trajectory should have the minimum distance to the final GPS target among these 5 candidates. And to follow the waypoints, we use adaptive on as local planner. And as the video shows, the lighter color means the higher confidence, and darker color means the lower confidence. And from the top left figure, we can see the selected trajectory during the current motion. And from the top right figure, we can see the third-person view. And the top middle figure shows the entire trajectory from the starting position to the far target. And the global trajectory has a length of 350 meters. And from the video, we can also see that the generated trajectories can ignore the dynamic obstacles, and they can also cover the most traversable areas.